In Chemical Equilibrium 3, I'm going to teach you how to write equilibrium expressions. First, let me define the equilibrium constant, which is denoted with a capital K and a subscript EQ for equilibrium. Now, before I read this to you, I must warn you it is a bit convoluted, but I promise you I will explain all of this. The equilibrium constant is the ratio of the mathematical product of the concentration of the products for a given reaction to the mathematical product of the concentration of the reactants for a given reaction. Okay? I have used brackets in this definition for concentration. So we're looking at concentrations of products over concentrations of reactants, and this is much easier to understand when we start to look at some examples. An equilibrium expression in itself is the formula for the equilibrium constant. It's in terms of concentrations in molarity of reactants and products. Let's look at this generic chemical equation in which the lowercase letters represent chemical coefficients and the capital letters A, B, C, D represent different chemical species. The rates of the forward and reverse reactions are the same at equilibrium. We've established that so far in the last two videos. We've also established the fact that the concentrations of all the substances remain constant for a system in dynamic equilibrium. Each of the concentrations, and when writing equilibrium expressions, is raised to the power of the coefficient. All right? So these are the steps for writing an equilibrium expression for the equilibrium constant. Again, you're going to take all of the coefficients and you're going to raise each chemical to that power. Again, let's look at an example to make things a little easier. Let's write an equilibrium expression for our equation here. So the equilibrium constant, K subscript EQ, is equal to, well, first we're going to look at our products because it is the concentrations of these products divided by the concentration of these reactants. These coefficients will become superscripts. So we're going to raise this to the power of C. We're going to raise capital D to the power of D. If it's a 1, you don't need to show that. Anything raised to the power of 1 is just itself what it is. 2 to the power of 1 is 2. So you don't need to represent that. Let's look at this. So we have C raised to the power of C, D raised to the power of D. That divided by the reactants. So you can see that the definitions for writing equilibrium expressions are far more convoluted than the actual mathematical expression. All right, so we're going to get a little practice doing this here. And for this example, we're going to consider first and foremost what can affect chemical equilibrium. What can change this equation? What nullifies, makes this equation not hold true? The answer is very simple. Temperature. Any changes in temperature will change the equilibrium expression because it's defined as the rates. We're looking at the rates over time. We're looking at forward and reverse. And if temperature increases, the rate increases. Temperature decreases, the rate decreases, which means that our expression is no longer valid. Let's do a practice problem. We have 0.19 moles of nitrogen dioxide. And we have 0.64 moles of dinitrogen tetroxide. And they're at equilibrium. They are inside of a 250 milliliter flask at 92 degrees Celsius. You are asked to write an equilibrium constant. What is the equilibrium constant for this reaction at 92 degrees Celsius? Notice the stress. I'm really accentuating this because if that temperature is not specified, you cannot write a chemical, an equilibrium expression. So in order to find and calculate the equilibrium constant, we need to write an equilibrium expression. Given our chemical system here that we've been studying throughout the past 3 videos, you're going to consider these coefficients, these mole ratios. And remember, it is going to be the products over the reactants. It's that mathematical ratio is the technical definition here. So we're going to have the concentration of dinitrogen tetroxide over the concentration of nitrogen dioxide. Remember, that's that reddish brown gas that we looked at in the last podcast. However, it's raised to the power 2. That is because there's a coefficient 2. So it is squared. We've taken it to the second power. All right. Now, concentration is expressed in molarity. And molarity, recall, is moles over 1 liter. And so we're going to need to convert these quantities, these molar quantities, into concentration. For that reason, the concentration of dinitrogen tetroxide is 0.64 moles divided by 0.25 liters. Recall, this is occurring in a 250 milliliter flask, which is 1/4 of a liter or 0.25. So you have to convert this into the liter because that is the SI units for molarity, moles per liter. Okay, let's do the same here for nitrogen dioxide, 0.19 moles divided by 0.25 liters. And now we have our molarities, our concentrations. Now we're ready to plug these into our equilibrium expression. So in the numerator, we have the concentration of the dinitrogen tetroxide. In the denominator, we have the concentration for nitrogen dioxide to the second power. The result of this computation gives you an equilibrium constant of 4.4. Let me provide a bit of intuition for what this value even means. You can calculate it, but this is worthless if you don't understand what this particular equilibrium constant value of 4.4 even means. All right, so let's take a look. If the equilibrium constant is greater than 1, this means that the products are favored. Think about it. If you get a value greater than 1, that means your value that is in the numerator of the fraction, the numerator, is greater than that of the denominator. So it's greater than 1. Products are favored, which means the concentration of the products is greater than that of the reactants. Remember, we're in dynamic equilibrium, where the concentrations of reactants and products is not changing, remaining constant. So this value is telling us that when this is in dynamic equilibrium, there's a greater concentration of dinitrogen tetroxide than there is nitrogen dioxide. When your equilibrium constant value is less than 1, that means the reactants are favored, which means that you have a larger value in the denominator, which gives you a KEQ that is less than 1. And intuitively, when it is equal to 1, that is saying that the concentrations of the reactants and products are approximately equal for an equilibrium constant value of 1. Okay, so in this video, I taught you all about the equilibrium constant. I taught you how to write equilibrium expressions. And lastly, what the equilibrium expression represented about the chemical system in dynamic equilibrium. I will see you guys in class.